Right now in the solar system, there are around 1,500 asteroids that scientists have identified as a possible threat to Earth. But it's thought there could be millions of asteroids out there that we haven't even found yet.
Detecting potentially hazardous near-Earth asteroids is now a priority for astronomers.
And asteroids have been hitting our Earth for around 4 billion years. Most famously, the Chelyabinsk asteroid wiped out the dinosaurs and transformed life on this planet. Even in the past few months, we've seen asteroid fragments hit the Earth in northern France and Texas. The threat clearly hasn't gone away. This year marks the 10th anniversary of one of the most terrifying asteroid impacts in recent years, the infamous Chelyabinsk meteor flash. On the 15th of February 2013, a 10,000-ton asteroid entered the atmosphere over the Russian city of Chelyabinsk. It exploded with 30 times the energy of an atomic bomb, injuring 1,600 people. And we didn't see it coming. Professor Alan Fitzsimmons is an expert in the observation and measurement of asteroids. He's one of the scientists trying to make sure we don't miss the next big impact. Now, I want to start with some jargon busting, because there's a lot of stuff out there. There's asteroids, there's comets. Can you take us through that?
Sure. Asteroids, like good old Bennu here, are objects, rocky objects that orbit the sun, just like planets do, but they're much smaller. We also have comets, of course. Now, there aren't as many of them, but they are very different. Comets have a lot of ice in them. Now, if that asteroid enters the Earth's atmosphere, then we see it glowing as a meteor or shooting star. If they make it to the ground, that is called a meteorite. And here's one here.
They're always far more dense than I would anticipate. So how are you monitoring the asteroids out there?
This is one of the Atlas telescopes. This one's in Hawaii. It's designed to pick up small asteroids that may be heading towards Earth on an impact trajectory. And down below here, we can see some of the images it's taken in the past 10 minutes.
So this is the early warning system, then flags it up for sort of further investigation.
They detect in total about 8 new near-Earth asteroids every 24 hours. It's amazing. So far, they have found over 31,000.
Of these near-Earth asteroids, around 1,500 have been identified as potentially hazardous. So what asteroid should we be worried about right now?
Well, there's a few up there, and one that's been on the risk page for almost 20 years has been the asteroid Apophis, and you can see it here.
Oh, right.
In fact, in 2029, on Friday the 13th of April...
It would be Friday.
It would be. It's going to make a very close approach. We're worried about it because we know it will miss us then. It's going to miss us when it returns in 2035. But it keeps coming back, and it's about 250 meters across. So that if it hit, this would wipe out a small area of the Earth. You know, something the size of a county or even a small country would really feel those effects.
Wow. It's reassuring that Alan is monitoring these potential threats so closely. But what I want to know is why some harmful asteroids still get missed. One of the most recent sort of devastating impacts was Chelyabinsk. Now, why didn't we detect that before it actually hit?
Well, there's a couple of reasons. First of all, Chelyabinsk itself approached on its last trajectory from roughly the direction of the sun, where our ground-based optical telescopes can't look, of course. Now, we could have tried to find it on a previous orbit, but Chelyabinsk was really small. It was only 18 or 19 meters across. It was just too faint for us to see. Objects the size of Chelyabinsk and larger, there's probably about 1 million, and we are still very inefficient at detecting near-Earth asteroids in that range. So these small objects, although they don't wipe out whole species, like happened with the dinosaurs, they hit much more frequently. Chelyabinsk, it injured 1,600 people. And we really do want to be careful to try to catalogue as many of them as possible.
The priority now is to detect these smaller near-Earth asteroids before it's too late. Thankfully, the technology is catching up. In 2025, the Vera Rubins Observatory will give us the widest ever view of our skies. And in 2025, NASA will launch a new orbiting mission, the Near-Earth Object Surveyor.
We hope within about a decade to have swept up most of the potentially hazardous asteroids in our sights.
So we should be confident.
I think we should be confident, but we shouldn't relax at all. We are still finding new near-Earth objects every day, and we know at some point in the future we will be hit again.
Tracking these asteroids and understanding the risk they pose is hugely important. But the next step is knowing if we could actually stop one if it placed us in harm's way.
Planetary defence has taken a great leap forward in the last few months, thanks to the DART mission, otherwise known as the most impressive snooker trick shot in history.
And liftoff of the Falcon 9 and DART.
NASA's Double Asteroid Redirection Test, or DART, was an experiment to see whether we could redirect an asteroid by intentionally smashing into it. In September last year, the DART spacecraft reached its target, the harmless asteroid Dimorphos.
Oh my goodness. 8, 7, 6,
wow.
5, 4, 3, 2.
It crashed into it at more than 13,000 miles per hour. And for the first time ever, we deliberately changed the orbit of a planetary object. I want to know whether the success of DART means that we'll be safe when an asteroid poses a real threat to life on Earth. Professor Simon Green at the Open University was involved in the preparation for this mission.
So Simon, what was DART trying to do?
Well, DART was designed to deflect an asteroid by using what's called the kinetic impactor process. So it uses a spacecraft to hit the asteroid and change its velocity ever so slightly so that it changes its orbit. And if this were a real impactor that was going to come and hit the Earth, it would eventually make that asteroid not hit the Earth by changing its orbit.
So this sounds like something that's pretty simple.
In principle, it is very simple, but in practice, it's much more complicated than that, as you can imagine. The surface of an asteroid will look something like this. It's called regolith. It's a powdered material with larger pebbles in it.
So we're hitting a rubble pile, not a solid object.
And it will throw off particles that change the way in which the asteroid will respond to the impact.
The composition of the asteroid determines how it will behave when the spacecraft hits it. Simon tests this in his lab using different materials.
This is our momentum stage, and it's essentially a bucket on springs. And it allows us to measure the momentum transfer when a spacecraft, here it is, hits an asteroid, which in that case is made of wet sand.
Okay.
So let's see what happens, shall we?
Bullseye! And it just sat there.
Yes, because the wet sand absorbed the impactor, the spacecraft.
When the ball hits the target made of wet sand, it should stop dead.
I'll just give you the ball back first. So here you go.
Next, Simon tries a material that is much more like the composition of an asteroid like Dimorphos.
Let's make sure I get my aim right.
Whoa! We got ejector, stuff thrown up. You can see this is bouncing much more this time than it did with the sand.
When the ball hits the gravel, ejector is thrown away from the surface. Physics says that the more ejector there is, the more the target is pushed in the other direction. This is called momentum enhancement.
That amount of momentum carried by the ejector has to be balanced by extra momentum in the asteroid moving in the other direction.
So it's just like how a rocket works. You throw stuff out one way and the rocket goes up.
Exactly. And that's called the momentum enhancement, this magic beta factor.
Right, and that's
that everybody
what we saw
wants
with
to
DART,
know.
right?
Yes.
When DART hit Dimorphos, the energy from the impact led to a crater being formed. And material from the asteroid was blasted out into space. This caused momentum enhancement, also known as the beta factor, and helped to propel the target further. It's the reason that a light spacecraft weighing only half a ton was able to change the orbit of Dimorphos, thought to weigh around 5 million tons. Simon's colleague Zoe Emerland uses a high-velocity impact gun to calculate the beta factor at higher speeds in the lab. Zoe fires an impactor at a target at 4 kilometers a second.
So this is what we get from the gun?
Yes, and you can see the ejector.
Oh wow. Do we know how much of an extra kick the asteroid got from this momentum?
We know that it gave a significant extra kick. DART mission was an incredible success because its first objective was to demonstrate that you can target a spacecraft onto an asteroid, hit it in the place you intended to, and deflect the asteroid. The impact produced a change in the orbital period by 33 minutes.
That's quite a lot.
Now, if there were no momentum enhancement, that would have given you a 7-minute change in the period.
But though momentum enhancement is useful, accurately calculating it is hard, as you need to know the composition of the asteroid.
It's good because any momentum enhancement you get means you get a bigger deflection for the size and speed of the spacecraft you hit. It's bad because you don't know how much it's going to be. When we find an asteroid that's going to hit us, we have to send a reconnaissance mission to measure its properties. So we can then adjust those models to precisely that body.
And then
we'll know exactly what spacecraft we need to hit it, how early we need to hit it, because we'll be able to make a much better guess at what the momentum enhancement will be. What is really, really important is that we find it early. If we get it late, we might end up in the scenario where we have to launch several DART-type missions and hit one after the other.
Right.
But of course, that is even greater risk.
If you look at movies and science fiction, people send bombs and all sorts of things.
They do, and I have to say that if you don't get enough warning, the asteroid is too big, then there is the potential to use a nuclear standoff weapon. Nobody wants to do that, okay?
Right.
But if it means survival of a country from total destruction, then, that has to be in our planning.
Yeah.
But it is an absolute last resort.
So nonetheless, you sound quite cheerful about where we are with planetary defence. So what I'm hearing is it's going to be our fault, us astronomers who look at the sky, not you planetary scientists. But if we don't find the things early enough, you can't help us.
We have to find them early enough, yes.
Right. I find DART really inspiring. Having realised there's a threat from asteroids, humanity has pulled together and gone a long way to solving it. It's an effort that's involved astronomers with telescopes finding the asteroids, lab work like we've seen today, complex computer simulations, and some excellent spacecraft engineering. Together, it's a potentially world-saving and fabulous effort.
But to really figure out the asteroids, we need to understand their origins, and, surprisingly, the role played by the largest planet in the solar system.
I remember in 1994 looking at Jupiter with my small back garden telescope and seeing giant bruises appear on the planet's surface. They'd been hit by Schumacher-Levy 9, a comet that got too close to it and had broken up. And as each fragment of comet hit the atmosphere, it sent up plumes of material thousands of kilometers high. It was a reminder of the dangers of living in our solar system. But Jupiter also has a role to play in the major threat to us here on Earth: asteroids.
At the time of recording, there were 1,264,630 known asteroids, with billions more still to be added. 650 near-Earth asteroids have been added this year alone.
Most of them live in the asteroid belt, a region between Mars and Jupiter, and while they stay there, they're no threat to us at all. Why are they there? Blame Jupiter. When the planets were forming out of a disk of gas and dust that surrounded the young sun, the giant planet's gravity seems to have stirred up this region, so the asteroids couldn't coalesce into one large world. So instead of a new planet, we get an asteroid belt. Science fiction makes asteroid belts seem like scary places, like your ship might be hit by a rock at any moment. But actually, there's plenty of space. The average distance between large asteroids is perhaps 1 million kilometers. If asteroids stayed in the asteroid belt, there'd be no threat to us at all. And yet we see tens of thousands of near-Earth objects, asteroids whose orbits cross our own and which might one day hit us. Why are they there? Blame Jupiter again. Its gravity is still stirring up the asteroid belt and altering the orbit of these asteroids so that they travel into the inner solar system where they might pose a threat. But Jupiter does do one good thing for us. comets and other bodies coming in from the outer solar system are much more likely to encounter Jupiter than anything else, and it almost always sends them shooting out of the solar system. So Jupiter today acts as a vacuum cleaner, keeping the solar system clean even while it stirs up our neat and tidy asteroid belt.
As well as playing havoc with our risk of getting hit by an asteroid, this month, Jupiter can also be seen in a rare event in our daytime skies. Here's our local stargazing expert, Pete Lawrence, to tell us all about it.
This month, on May the 17th, there's a very rare daytime event, a lunar occultation of the planet Jupiter. That's when the moon appears to move in front of Jupiter during daylight hours.
The last time we saw this in the UK was on the 15th of July 2012, and the key to spotting it will be to locate the moon in the daytime. We sometimes see the moon during the day for the same reason we see it at night. It is reflecting light from the sun. I'm going to demonstrate why it's sometimes easier or harder to see in the day using a few props.
The amount of the moon's surface we can see illuminated depends on the angle between the sun, the earth and the moon. As the moon moves around the earth, we experience the lunar phases. So we go from a crescent round to full moon when it's opposite the sun in the sky, and then back round to a crescent again.
The best time to see it during the day is when it is waxing or waning gibbous, so between half lit and fully lit. This is because a big area is illuminated and it's away from the sun's glare. But when it moves between Earth and the sun, like during a new moon, it's completely invisible because the illuminated side faces away from Earth. So whilst it's surprisingly common to see the moon during the day, it is an incredible opportunity to see Jupiter passing near or behind it on the 17th of May. As this is a daytime event, it's very important that you don't look at the sun with a naked eye, telescope or binoculars. One way to stay safe is to stand in the shadow of a building so the sun is hidden. Jupiter is the largest planet in the solar system, 11 times larger than Earth. It rotates 2.5 times more quickly than Earth, which gives it a squashed appearance through the telescope. And it has at least 92 confirmed moons, more than any other planet in the solar system. On the 17th of May, the moon has 2 key positions to locate it before the Jupiter occultation at 3 p.m. At 11:24, it's due south, halfway up the sky. Its phase is very thin, so it's quite hard to see. Jupiter will appear to the left and up a bit from the moon. Otherwise, at 13:40, the moon will be due southwest, just under halfway up the sky. Through binoculars or a telescope, you'll see a ghostly Jupiter closer to the moon's crescent. For those south of the Scottish border, Jupiter makes a close pass of the moon at 1500 BST. But those in Scotland and Northern Ireland will see a true occultation from about 1435 onwards. The time changes depending on your location, so it pays to start earlier if you can.
If you're lucky enough to capture the occultation, we'd love to see your pictures. Upload any images to the Sky at Night Flickr and we'll pick our favourites and show them in next month's show.
Over the last month, you've been sending us your fabulous images of Venus and the Hyades and Pleiades.
Asteroids can pose a serious danger to life on Earth, which is why they're monitored by scientists across the world. But this work isn't only carried out by experts. There's also a network of amateur astronomers helping to track the meteors in our skies. One of these meteor trackers is Mary McIntyre.
I love doing the meteor science because it's amazing to just be part of a community that are just doing so much amazing work. It's helping with meteorite recovery, it's helping with planetary defense as well. And these cameras are basically low-cost CCTV cameras, but for space.
Mary is part of a global network of over 450 cameras. And it's something that you can set up in your own back garden.
These cameras are so accessible now. The Global Meteor Network system is using a Raspberry Pi computer, which is fairly inexpensive, and the software that does all of the science is free.
There's information online about how to set up your own meteor camera. You'll find a link on the Sky at Night webpage, and you can also buy a pre-set up camera system.
The best place to mount the cameras is somewhere very sturdy, so it could be the back of a house or a solid wall, or it could be a shed wall like ours. And then you kind of want the camera pointing up at about 45-degree angle. You just never know when an interesting event's going to happen, so never ever turn them off.
The camera's observations of a meteor automatically collate with others onto the Global Meteor Network.
These cameras capture a huge amount of data. It will tell you how fast it was going, the angle that it came in to Earth's atmosphere at. It will tell you the orbit, so you know exactly where in the solar system or even extrasolar system that these events have actually originated.
The majority of meteors that we observe are seen as streaks of light that burn up in the Earth's atmosphere. But sometimes we see a fireball, a really bright meteor that survives the Earth's atmosphere and can land here on Earth as a meteorite.
I think it's just the most exciting news ever when we discover that a fireball that's been picked up on our cameras has resulted in a meteorite fall that has been recovered.
Amateur meteor trackers like Mary playing a major role in the study of how asteroids may have helped to kickstart life on Earth rather than destroy it. On the 28th of February 2021, a bright fireball was spotted in the skies above the UK. And it's led to new ideas in understanding the early solar system. Astrophysicist and exoplaneteer George Dransfield is at Royal Holloway to find out more.
This fireball was so significant because it was caught on UK Fireball Alliance cameras and they were able to track its trajectory. They could see that it was headed towards Gloucestershire, specifically in and around the town of Winchcombe. And crucially, this meant that scientists could get to the right place immediately and gather up all the fragments.
600 grams of blackened debris was picked up from people's gardens and driveways and local fields.
Are you sure? Yeah.
Oh, yeah, it totally is.
That is
totally
very
is.
obvious.
It was a truly historic moment. The first time in 3 decades that a meteorite has been observed hurtling across the UK and then recovered, ready for analysis by scientists around the world, including planetary scientist Dr. Queenie Chan.
Why is it important and significant when we find a meteorite?
Asteroids are the building blocks of planets. So we get to see how the planets was formed at the beginning of our solar system.
Okay, so they have like a fossil record of like early solar system. And what is particularly special about the Winchcombe meteorite?
Over here, I've got tiny pieces
Yeah?
of the Winchcombe meteorite. It's very exciting for us because it's been recovered really quickly after it fell. So we want a clean meteorite, not as contaminated by the Earth's atmosphere, but also it's a kind of carbonaceous or carbon-rich chondritic type of meteorite, a rare type of meteorite that's been recovered on Earth.
Carbonaceous chondrites are some of the earliest materials in the solar system. Older than the Earth, they could hold the answers to what molecules were present when life on Earth began. Queenie has another example of this rare type of meteorite to show me.
So here I've got an example of that, and it is called the Murchison meteorite. It's a famous meteorite that fell on Earth in 1969. Meteorite
That's a
here.
piece of space rock!
Yeah, so if you look closely, can you see the white specks? And they're quite rounded.
Yeah.
So they are called what we call the chondrules. So chondrules are one of the first solid that's been formed at the birth of our solar system.
Queenie has been analysing the Winchcombe meteorite, looking for what molecules existed at the very beginnings of the solar system. Her focus is on amino acids, the building blocks of life.
So you've been working away at this and scraping bits off and studying the Winchcombe meteorite. What have you found?
And we found that there are a range of amino acid molecules in the Winchcombe meteorite. It's quite exciting. Some of them are even protein-forming type of amino acids. So the fact that we have found amino acids in Winchcombe is a big deal because we need those molecules for life to occur. And the reason why it is so exciting is because there are two theories of where Earth's molecules of amino acid were from. So it's either that it's been totally Earth-based, so it was all created by reaction on the Earth's surface, or it could be delivered by asteroid from outer space. And we know that both are possible.
As well as these building blocks for life, scientists have found evidence of water in samples of the Winchcombe meteorite, with a chemical composition similar to that on Earth. This adds weight to the theory that asteroids could have delivered the ingredients for life to our planet. And it means that these same ingredients could also have been delivered elsewhere in the universe.
Hang on a second. Are you telling me that potentially life on Earth is extraterrestrial in origin?
Well, it's quite an interesting topic because life on Earth, I don't know whether they're extraterrestrial, but we definitely know that the ingredients that need to form life, or ingredients that life needs to exist, can be coming from outer space.
We do often think of asteroids as a bit of a threat, perhaps because of the whole dinosaurs incident, but we are learning more and more about how asteroids might have also contributed to kickstarting life on Earth. And what was mad cool about this incident in particular is the way citizen scientists helped track its trajectory so that we could collect it and then do some in-depth science with it in our labs.
That's it for now, but do join us next month, where we'll be investigating the latest science and engineering of rockets.
Until then, good night.